Welcome, everyone. I'm your host, Eric Novick, and I'm very excited to have Jessica Hullman from the Department of Computer Science and Engineering and Middle School of Journalism at Northwestern joining us today. Welcome to the program, Jessica.
Thanks for having me.
Currently, you're doing some research on uncertainty representations, which we'll get into in a little bit, but you're once studying critical aesthetic theory. And critical aesthetic theory is a kind of sentence where I know what every one of the words mean, but I have no idea what it means in concert. So what is CAT? What did you find it attractive and then ultimately decided to give it up?
Yeah, that's a great question. I guess just more generally about me, I was always sort of pulled between both like science and really analysis. Like I always loved stats and like art on the other hand. So I always was really interested in trying at some point in my life to become like a writer. And so I did an MFA after undergrad where I did like experimental writing. But during that time, I found that I already wanted to get more analytical than like most people who are doing art do. And so at that time, I started getting into like what's called critical aesthetic theory, which is, it's almost like philosophy of art. So there's like history of art, which is kind of like, what did like Dada mean as like a cultural movement, or like why did kitsch come about and what does it represent? Whereas so that's like art history, but like a critical aesthetic theory, it's kind of like more philosophical. So it's more about, like what is the role of art in society? Like what are artists trying to represent? I remember part of it was like, that I recall at least was like, they'll talk about sort of like how art has evolved over time and theories about like, has art lost its ability to productively function in society? So I remember that one of the things I got into was like these theories that like contemporary art, like after we move past modern art, contemporary art is now defined not by like the content of like the piece of work, some experimental painting, whatever, but it's defined by what it is not. And so a lot of it, I guess, gets into like semiotics, like and in some ways it makes sense now to me, like looking, even though that's so different from what I do now or what I've been doing for years, really. In some level, it makes sense because I think a lot of what I think about is like, how people make meaning from different representations and like, what is it, like how do we ascribe meaning to things? And so I think it's kind of, philosophy in that sense, but applied more to art.
Interesting.
Great question. Something I haven't thought about in years.
Okay. But then you eventually sort of decided to pursue something more quantitative. That's what led you, I suppose, to this research in the uncertainty representations. And like I said, I always liked stats. I just found that I missed it too much. I took a few years and tried to do the art stuff, and it was just, I kept getting more analytical, and so I was like, okay, I should just get this up. Yeah, I see. It was hard to make friends with all the artists when all you want to talk about is stats.
Exactly.
All right. In terms of uncertainty representations, what are those? Is that mostly related to visual representations? Is that right? And what does the research in that area look like?
I think I use the word uncertainty representations rather than uncertainty visualization, in part as a reaction, I think, to like my field and how we think about it. So I'm most associated with the research community of interactive visualization, which is like mainly computer science, but sort of more and more interdisciplinary. And there we talk about uncertainty visualization. And, in visualization research, we often really focus on like the visual encodings. So like, what are the different ways I could show a distribution? Like I could map probability to like opacity or like height in a density plot. And so I think when I think about uncertainty and like everything I've learned from my research, coming up with these techniques and then like testing them, is that it's often like what matters when you're trying to, represent uncertainty in any sort of visual interface is often not just like the visual encodings, like exactly how you show it, but like the underlying way in which you're trying to represent uncertainty. Like how are you computing it? Like, are you a frequentist? Are you a Bayesian? Like what's the underlying interpretation? Are you going to show an interval, or are you going to show a full distribution? So like, I think I use representation just because it feels like what actually matters is often not the specific visual parameters, but like the bigger picture of like, what do we think we're saying with this representation of error or probability or whatever.
Interesting. Makes sense. So now you mentioned this, frequentist versus Bayesian, and those are slightly different views, or maybe not slightly different views of uncertainty. And a lot of your work had been rooted in Bayesian context, but is that exclusively the domain of Bayesian? How do you think about those things, and maybe how you got introduced to Bayes in particular, and is it useful or helpful, or are there other ways that you think about the uncertainty?
Yeah, I think I got introduced probably in undergrad, and I just remember whenever like Bayesian, analysis or Bayesian reasoning came up, I always like really like found it compelling, and I think. But then I didn't really start getting into like reading, like the Bayesian philosophy versus frequentist philosophy until probably grad school. And like many of us in my grad program were like, religiously reading Gelman's blog. And so I think that's where I started to get into it. And I guess in so many ways, like, it sounds silly, but it just so much aligned with the way I think about like data and how people, I think a lot about like, how do people reason with data? And I think it's like a natural framework for trying to explain how we interact with data in a lot of ways. And so I think, I read a lot of Gelman blog, and it just like a lot of my ideas, even early on as a PhD student, about like how we could design better visualization interfaces, et cetera, like were just sort of influenced by me reading a bunch of Bayesian stuff. So yeah, I think I try not to like jump too far into these like debates that sometimes go on Gelman's blog about like, like at the core, like how different is the frequentist model, and like, like, can we ever really be sure about any prior that we have? But like, I don't think like Bayesian is the only answer by any means. I've worked a lot with Matt Kay, who's like a better Bayesian statistician than I am. Like he really loves just like doing Bayesian stats on data. I think I'm more interested, like I like Bayesian stats, but I'm more interested in it, sort of a framework for trying to like think about how we're developing things. But yeah, I almost now worry in my field, like now more and more people are doing Bayesian statistical analysis, in part because people like Matt, and then I started. And so like now I almost worry that more about like people having sort of, just like seeing Bayesian stats itself as like a better way to do stats, when in reality, I think, like often if you're using like, uninformed or weakly informed priors, you're getting the exact same thing. And so I think it's a good tool, but I'm not gonna like die for Bayesian stats or like,
you're not a religious Bayesian,
no,
like me. Okay, that's fair.
Yeah. Don't ask me any questions about like, the deep stuff, because I don't want to go there.
Fair enough. So perhaps as a little bit of preview into what you're going to talk about, as I was reading the paper, you make this distinction, specific distinction between exploratory and confirmatory analysis. Those terms may not be familiar to everyone, so perhaps you can explain that a little bit, and then we'll roll into your talk after that.
Sure, yeah. I'll say more in the talk, but yeah, I think if you just like read about characterizations of the statistical process, there's often, if you're doing some sort of statistical inference, we often, think about like, well, first you get your data, and a lot of this is how we frame it in visualization research too. Like you get some data set and you do this exploratory phase where you're like trying to find the patterns in your data. You're checking distributions. You're doing like basic data diagnostics to see like, are there any errors? Like, is this data what I think it is, or am I going to be surprised because I'm like, I have missing data, et cetera. So this exploratory phase is often, and this comes up in science reform too. People debate this, but like it's this idea that we're not really thinking about probability necessarily. Like we're just looking at what we have in the data. We're maybe like generating hypotheses, but we're not yet trying to test any hypotheses. We're not doing any formal statistical modeling. And part of like the replication crisis, like is some people attribute it to the fact that researchers are presenting exploratory analysis as confirmatory. And so, I don't have to explain this to you because you have like a paper on the Garden of Fork Pass or whatever, but this idea that if we're exploring things, we have all these degrees of freedom. We haven't pinned ourselves down to any particular hypothesis. So it's easy to be like finding and seeing patterns. And in visualization, I think we often more associate our visualization tools with exploratory analysis than, and then on the other hand, confirmatory analysis is like what you learn in like a lot of the stuff in Stats 101, like what's a t-test, a null hypothesis significance test, like you're developing or specifying some sort of model, and then you're testing how well your model describes the data that you have. So a lot of this paper is partly a critique, or it really, it's more like posing this question of like, where do we think visualization most belongs? Because as I'll talk about in the talk, like, I think if we look at the way we build a lot of these graphical user interface visualization tools, it's almost as though we're sort of assuming we're always in like exploratory analysis land, where we don't have to worry about uncertainty and probability necessarily. Like it's all just like pattern finding. But I think in reality, like, and I really like some of the more recent science reform sort of philosophy stuff, it's very hard to actually distinguish these things other than that, like confirmatory analysis. Like it's hard to draw a sharp line between like where one phase ends and the other starts, because there's often loops. And the only thing we can really say about confirmatory analysis is that it comes after exploratory analysis. But so I'll say a little more in my talk. But.
Great. Okay. So it's, if we can sum that up, it's a sort of pre-model, an analysis that is sort of precedes the model development and the model, and the analysis that supersedes it, right?
Yep.
Something like that. Okay.
Yep.
Very well. So with that, let's. I'm going to turn it over to you. For everyone else, as Jessica is talking, feel free to put up some questions in stage chat, and we'll collect those questions, and then at the end of the talk, we'll have a session of Q&A. Please take it away.
This is a paper, or this talk is related to a paper. I'll cover various things from my work across the last 5 years, but there is a paper associated with, I'll put the title up at some point, that I wrote with Andrew Gellman, calling this talk Theories of Inference for Data Interactions. And my research interest, as someone who's, kind of a computer scientist, but interdisciplinary, really revolve, I think, around the role of data in judgment and decision-making. And in particular, visualization interfaces have always interested me because they directly influence, I think, how we think about data, how we interact with it, and, how we interact with various predictive systems. And I'm interested in, how we interact with data and predictions in these daily life settings to, settings like I'll talk about more about today, like where we're doing visual analysis, using different tools, maybe for business intelligence or for government analysis. And I'm also interested in, how we use visualization and how we represent data in the scientific literature. But like I said, while my work covers all of these in various ways, today I'm going to focus on this middle bucket. But first, more broadly, before I say more about these graphical user interface tools, I think it's useful to know, like something basic about why we often gravitate towards visualizations when we're talking about representing data or model predictions. And this is based on this ability that visualizations have to offload cognition to perception, as we like to say, and make it easier to identify patterns and relationships. So, for example, maybe many of you have seen Anscombe's quartet, this set of 4 data sets that would look identical if we were to summarize them with summary stats alone. But, when we plot them, it's quite immediately obvious that, they have different signatures, different distribution of points. And so in the last few decades, research on interactive visual interfaces has broadened, I would say, from initially being this research field that really cared about, making interfaces like powerful visualization interfaces for, expert analysts who do analysis all day long of certain types of, point pattern data or geographical data, to now thinking more and more about this larger range of settings where people are trying to analyze data and communicate data. And yet I would say that despite sort of the progress in this field of research, where we're broadening the scope, when it comes to how we sort of talk about and think about the real function of visualizations and visualization systems to support analysis, it's often pattern finding that we focus on or that we talk about. I think this notion that visualization is mostly just about exposing patterns in our data may be a carryover from the way that interactive infoviz as a discipline was born, where we were inspired greatly by pioneering efforts in exploratory data analysis by John Tukey and other statisticians. So Tukey was kind of tired of the way stats back in his time was dominated by formal mathematical proofs of confirmatory analyses techniques like hypothesis testing. And so he popularized this idea of exposure, or using graphics to understand what's in our data in the first place, before we know exactly what we're looking for. And, he talked a lot about how graphs help us see what we didn't expect. And this might have encouraged this view, that exploratory data analysis and visual analysis are kind of model free. EDA, has this this emphasis on exposing the patterns, maybe generating hypotheses. And this is difficult to reconcile with more confirmatory sort of formal statistical testing approaches. So for instance, it's not clear whether all of the activities that happen in EDA, like hypothesis generation, belong in any sort of probabilistic framework. And I think Tukey was very aware of like this tension, like what exactly is exploratory analysis? And these questions are hard to answer, like what's the right integration or the right way to think about these two things. And so today, I think perhaps because these are hard questions, when we design visualization tools and when we use visualization, I think we often are simply sort of defaulting to this assumption that it's about pattern finding or communicating some signal like a trend or a difference. And we don't necessarily think of them first as tools for, statistical inference or decision making. If we look at, research in interactive visualization, which is the field that I've done most work in, there's all sorts of work coming out that we could say focuses on what some have called these behavioral optimizations. So we want to make the data as easy to see and access as possible so the user can find the patterns. And so we can do that by, developing things like touch or pen-based displays for interacting with data, or speech or language-driven querying of visualization interfaces, visualization recommender systems where you can simply say, like, here's the variable I'm interested in, and it'll recommend a bunch of views of plots of that variable and other related variables, as well as like learning from low-level interaction data, what plot someone might want to see next. And so all of these very sort of sophisticated types of optimizations seem to assume that we just need to like make the data readily available to the human analyst, and we can assume that they know what to do with it. And we don't need to worry about, necessarily modeling the user themselves or worry about like how their inferences from the data play out. You can just kind of trust them and serve up the data quickly and efficiently. Some of my work over the previous years has been sort of questioning, like, is it that easy? Are we, by sort of emphasizing pattern finding and pattern exposure, missing some important aspects of how visualizations work in statistical inference? And so some of my work, like I said, has looked at this. And so I'll give a few examples of sort of pitfalls in the way we study visualizations and build tools when we just think about them as for finding patterns. So one example that crops up is related to the defaults that we build into these interactive visual analysis tools and how these defaults might threaten the validity of inferences people are making from data. So many systems, including Tableau, which is, really popular for like business intelligence type analysis, are going to aggregate data by default. And they do this to enhance your ability as an analyst to find patterns in the face of big data sets. But many people and many businesses are using Tableau and other systems to analyze and communicate small data sets, so not millions of rows. A few years ago, we did a study where we asked novice analysts to generate observations about a population as they assess different statistical graphics of data. The data sets were of various sizes that we showed them, and we asked them to, say what sort of generalizations they thought they could draw about the population from the samples, and also to tell us how confident they were in those generalizations. And we either showed them aggregated data, like on the left, something like you would see in Tableau, or disaggregated data on the right, which is what a few visualization recommender systems default to. And what we found was that, when you have people working with aggregated data by default, they tend to focus more on what we call dichotomous thinking about differences. So in other words, people, their statements about the data, the things that they concluded, used a lot of language that implied, there either is a difference or there is not a difference. They didn't really think about things like effect size, like how big is this difference? How strong is this trend? We also saw that how confident people were in these statements that they were making about the data, how confident they were in those was not really affected by the size of the sample that they were looking at, which intuitively we would hope that, people are sensitive to sample size, but especially with aggregation, they were not very sensitive. They were more sensitive when you show them disaggregated data because you're implicitly showing sample size. So that's one example. I've also looked at things like, how do we research visualizations? How do we evaluate visualizations? Like, how do we know when we have a good visualization? I would say we lack kind of a deep grounding in terms of how we evaluate visualizations for telling whether a visualization's been useful for inference or for generalizing beyond the sample to some bigger populations. A few years ago, I looked at about 90 experimental evaluations of uncertainty visualizations, looking at sort of what behaviors the researchers wanted to change with better visualizations and how they measured the success of their visualizations. And I found that even in uncertainty visualization, which is all about emphasizing decision-making under uncertainty, the vast majority of evaluations are comparing, how accurately can people read the data in the visualization, or they're asking people, how satisfied do you feel with this visualization? How effortful did it feel to use this visualization? But very few were actually looking at like decision making or any sort of like belief updating from the visualizations. And so, the problem here is that, well, if we're all looking at like perception and satisfaction in order to judge when a visualization is useful, there's no guarantee that someone who can read the data is necessarily going to act on it. And there's also no guarantee that, when someone feels like the visualization is pleasant to use, that it's actually going to be useful for them. So just to give an example, many of you maybe saw the New York Times Needle on election night in 2016. It was this animated dial. And people hated this visualization. It was very effective at showing uncertainty. I think the problem was that, up until election night, we'd been seeing these visualizations that didn't do a good job of showing uncertainty, where it was very easy to sort of ignore the uncertainty. When people finally got an effective visualization, it was on a night when they were already anxious, and so everybody hated it. So there's no guarantee that people know exactly when they're getting a good uncertainty visualization. And in a lot of ways, we don't like to reason with uncertainty. Most people don't. And so, there's almost like a negative relationship, if any, between these things. So recently in my work, I've been thinking more critically about the role of visualization and analysis and what's missing in terms of our understanding of visual analysis and the way we build tools. And like I said, much of what I'll talk about today is related to a paper I wrote with Andrew Gauman recently. It should come out this summer in Harvard Data Science Review. It's basically a critique and kind of a vision paper for interactive visual analysis software, which I've been thinking about for a while and which relates to some earlier work that Andrew did on graphical statistical inference. Let's get into sort of what's the role of visualization and analysis. For many of us, I would say that do data analysis, probably many in the audience here, we might associate visualization with data diagnostics. We want to get an initial sense of, when we first get a new data set, of how things are distributed, whether there might be errors or missing data, where there might be strong correlations, perhaps. And, I think data diagnostics we can think of as closer to descriptive statistics, in that we simply care about like seeing what we have and describing the sample of data that we have. And there are other uses besides data diagnostics when we first get the data that we could also call purely descriptive. Sometimes we have a visualization where we just want to answer a question about the data. Like we just want to know what happened in the past. So for instance, people love sports data. This is an old school baseball visualization, but we could simply ask things like, well, which players in the last season had the most assists? And so this is kind of descriptive use of visualization. On the other hand, I would say that often, and perhaps even more often, when we use visualizations, when we see visualizations, in our daily lives, when we use them in our work, we care about making inferences from this data that we have to some larger phenomena in the world. So I might use the same baseball visualization, but I might ask a different question, like what sort of players should I invest in as a team owner? And so a question I'm asking these days is, how well did the interfaces we design support this more inferential use of visualization, where the goal is really, you could say, to think about the process that generated the data, or I'll call it the data generating process. But we want to go beyond just the raw facts in the data to thinking about the process that created it. And so if we're talking about drawing inferences from data, extrapolating from data to real world phenomena, then we should talk about like what is the analysis process for inferential data analysis. And so Tukey, back in the 70s, characterized analysis as beginning with this initial exploratory phase, which I talked about a little as EDA, in which the analyst doesn't really consider probability. In science reform, they sometimes talk about discovery-oriented research and associate it with what's called pure abduction, where we don't have any theories yet that would like strongly imply a testable hypothesis. We're simply trying to define like a space of possible things going on in our data, effects that might be supported. I think, like I said, in visual analysis and visualization, we often associate it with this phase. However, Tukey also talked about how there's this intermediate phase that's probabilistic, in which the analyst tries to answer this question: with what accuracy are the appearances or the patterns that I've found to be believed? And so there's potentially use of visualization here to classify, what kind of data problem we're dealing with. So Tukey described how you could have, these patterns or things that you perceive that are so poorly defined that they could just be forgotten. To things that are marginal. So maybe we can't do a crude analysis, but we have some pattern where we could do a more careful analysis and actually get some signal out of it, to cases where, we really don't even need to do formal statistical modeling because the pattern is so obvious. Visual analysis can therefore like play this role in classifying what kind of data problem we have, helping the analyst distinguish, what are you working with and how much more analysis do you need to do. And then this should be ideally followed by confirmatory analysis, where any of these patterns that we can't just rely on our eyes to judge have to be more carefully modeled. We have to test any hypotheses that we have more formally. And so the question, I'm asking is, well, how often can we assume that all of these stages are happening when we're designing visualization software, and especially these graphical user interface tools? Are we maybe focusing too much on this early phase and not really supporting these second two phases very well? So that's kind of an argument that I'll make. And of course, this is complicated, and I think Tukey certainly wasn't saying this is a linear process. There's all sorts of loops, and that's kind of what makes it hard, I think, to design software and to think about these workflows for analysis, because often you are jumping between things. You're going back to a more exploratory phase in some cases. So it's a complex process. Nonetheless, I think it's useful to sort of try to have this bigger idea of like what's the workflow when we're doing inferential stats. So, as a researcher in visualization, working on these kind of problems, it would certainly be easier for me if we could just assume that everyone who uses visualization tools to do any sort of inference is going through this entire process where everything they perceive initially in the visualization is getting more carefully modeled. But there's lots of evidence coming out that, and some of what I've talked about, with people drawing conclusions from aggregated data in Tableau, that suggests that like people are often comfortable drawing conclusions from visualizations alone. And so we can ask, on a sort of a theoretical level, if we have these three buckets of data problems, from the ones where the signal's so obvious that we don't really need to even model it at all, to the ones where the signal is so confounded with, or there's so much noise that we can't actually draw any conclusions, where do we think visual analysis belongs? And when we design tools, what do we need to give people in terms of functionality? We would think that if we have a huge signal to noise ratio, there's going to be some problems where we can just rely on visualization alone. We don't need to do any testing by sort of definition of these classes. So we're fine here with just visualization. But it seems doubtful that, most people or everyone using these visual analysis tools is always in this bucket. And so presumably, sometimes we have data problems where there's some noise or confounding. So we want to do some form of modeling. And so I think the question becomes like, well, do we need both visualization to help us identify that we're in this bucket and formal statistical modeling in order to sort of come to a valid conclusion? Or are there, potentially parts of this space of moderate signal to noise ratio where we could just use visual analysis? So these are kind of questions that are totally unanswered in the visualization research literature, but that I think we need more clarity on in order to build, better tools and use visualization better. So also related to sort of this relationship between visualization and confirmatory analysis, some statisticians have talked about how you can sort of associate a statistical question and even a statistical model with a graph. And I think Tukey would say that this kind of example, it falls into this intermediate stage, which he called rough CDA. So back in the 1990s, Becker, Cleveland, and Hsu talked about this relationship between a trellis plot and a statistical model where your trellis plot is set up to help you visually test for main effects. This is barley data. We have different types of barley, and we have different sites as the rows, and then we have data for 2 different years. We're basically testing for a main effective year, a main effective type of barley, and a main effective site with a display like this. And we can, if we know something about visualization, then optimize the visualization to try to make the perception of deviation from these expected effects more obvious or more direct. So for instance, we can redesign this initial trellis plot to put the 2 different years on a single axis so that it's even more obvious. And here in the paper, they use this example of this sort of visual modeling to show that like if you know what you're doing and you're thinking about like what you expect to see and you know how to use graphs well, you can actually do things like detect errors in your data and do these sort of rough checks for main effects. So there's some relationship often between certain types of graphics and certain types of models. And at the more sort of extreme view, some statisticians have proposed that when we look at a visualization, we're doing something analogous to a hypothesis test. So this idea goes back to Andreas Buja, a statistician, and was popularized in visualization research back in 2010 in a paper by Hadley Wickham, Diane Cook, Heike Hoffman, and Buja, I believe, where they proposed this technique called the lineup, where we have one visualization of some observed data. we are going to hide it in a lineup that also includes 19 visualizations representing what we would see if the null hypothesis were true. And the assertion that's made is that if the unknowing analyst can look at this lineup and they can pick out the real data from the lineup, then they've approximated a null hypothesis significance test with an alpha value of 0.05. And so, you can try to do this, like you can try to look for like, where's the correct data here? I'll give you a second to look for it, and then I'll tell you later. This techniques, makes this strong implication about, we can actually use visual analysis in place of formal statistics. And so this question arises, well, if, every visual examination we do of a plot is actually some form of hypothesis test, then do we need to worry about the multiple comparisons problem when we're doing visual analysis? So multiple comparisons problem just being the fact that the more hypothesis tests you do, the more inflated your chances are of thinking you found something when in actuality it was just a spurious or it was a symptom of random chance. And so some recent work in computer science is asking, well, like, how do you control for multiple comparisons in a visualization tool? Do you like fade the data out as someone's doing more and more visual comparisons so that they can no longer even see patterns? Like, how do we deal with this? Which I think is a really interesting question, and there's not a lot of answers. Okay, so if you were looking for the real data, I believe it's plot 16, and you can tell by just trying to see like where is the central tendency of site A and B the most separated. But this one is kind of hard, so don't feel bad if you, I guess, didn't get it. So anyway, so that's all sort of a summary of these ideas floating around about like what is visual analysis and how does it relate. In our paper, we don't really claim to know the truth about this, like how to best analogize visual examinations of plots to a statistical framework. But we propose that we need some sort of theories, like we need a better understanding of this so that when we're designing interfaces and thinking about how to use visualization effectively, we can be clearer about like what is successful in terms of using visualization in an inferential analysis process. And so if we don't make any attempts to formalize like what we think good graphical statistical inference is, then we're stuck relying on sort of pure empiricism where we're just like trying things out and hoping that something works. And that includes how we design tools. As computer scientists, we don't want to be like randomly developing tools without any clear like theory behind them, because it's just sort of a not very efficient way to learn about like, what's best. And so we ask in this paper, well, what is a good high-level theory of graphical statistical inference that could like inform our understandings of how we're using visualizations in a variety of ways when we use some of these like, graphical user interface tools. To introduce kind of the framework or the way we think about it, I already talked about this idea of some plots being analogous to statistical models, like the trellis plot that Becker and Cleveland and Shu proposed. Here's just some more examples. Say I'm using something like Tableau. I'm a real estate agent. I have some public housing sale data in my area. And I might construct plots like these and ask myself things like, well, on the left here, is there a main effective neighborhood in terms of housing sale prices? Like, should I focus more on houses in some neighborhood? Or I might ask, like, what's the relationship between the lot type and the sale price? And how does that differ across neighborhoods? I'm like visually inspecting, visually comparing things across these plots and trying to say like, well, how different do I think that like this trend is versus this? And then I might, also be looking for things like, well, how strong is this relationship between, the amount of square footage of above ground living area and sale price, as well as like square footage of above ground bedroom space. So I might be, sort of implicitly, looking for some sort of linear trend here, depending on the data. I might actually flip and start thinking, well, maybe actually there's something more parabolic. I might be looking for like a smooth gradient in terms of color as I go, higher on the x-axis and higher on the y-axis. So these are all kind of these implicit things that good analysts might do as they use graphics. In terms of like formalizing, like, well, theoretically, like what could we say is going on when people examine graphs? I think, if we're talking about graphs as sort of showing us what we didn't expect and helping us find what we are not expecting, we should think of our expectations as kind of what give graphs meaning. And so EDA, even though many people often describe it as kind of model free, even in the most basic sort of data checks, if we're looking for what's unexpected, we must have some sense of what is expected. And we can think of that as sort of a rough type of model in many cases that tell us, what should we see in this data? And so at a high level, we can imagine that people have some expectations when they look at graphs. those expectations represent what they expect to see, given what they already knew, maybe given what they notice about the data in the visualization, maybe influenced by what kind of chart type they're using. And they're going to be implicitly comparing their expectations to the visualized data. When we do this, we're basically trying to figure out from any visualization we look at, like, how much does this deviate from what I expected? And we might even go further and do something to sort of think about, well, how much deviation am I seeing? And is this an important amount of deviation? Like, have I learned something from this graph? And so in our paper, we at a high level say, well, we should think of people as having these kind of pseudo-statistical models in their heads that they're kind of checking against graphs. And that's how we use visualizations. And the more we can align our pseudo-statistical model with the design of the graph, the more useful the graphs are to us. And I say pseudo-statistical because, while we can think of someone's expectations about data as being a form of statistical model, when we're dealing with people and how they reason with data, there's no guarantees that people follow the laws of statistical inference, the way we might hope. There's some analogy perhaps to a statistical model in terms of what my expectations are of data. We want to think of that as not necessarily a perfect statistical model, but a model that we might compare against a formal statistical model in order to help people figure out where their expectations and where their assumptions about, how much information there is in data are wrong. So to just give a simple couple concrete examples, these are very simple examples. There's more in our paper, but, imagine I'm looking at a histogram. If the data are remotely bell curve shaped, maybe I'm going to start looking for deviations from normal. So I have this kind of implicit reference distribution in mind. If I see something very skewed in my histogram, I'm going to switch to some different reference distributions, like some exponential distribution. If I'm looking, at bivariate scatter plots, I'm probably, implicitly imagining a line of best fit in the simplest case, maybe something slightly more complex depending on the pattern I see in the data. This is sort of like how I'm doing my visual analysis. It's depending on these references that I have in my head. And we can observe that in many ways, like how well a visualization supports these implicit model checks tells us how good the visualization is. So some of the most effective visualizations that we see for formally checking model fit in confirmatory analysis are things like QQ plots or residual plots, which are designed in such a way that this reference model is almost like baked into the graph itself. So imagine, I ran some regression, I have some residual plot. If I know how to read a residual plot, I know exactly what I'm looking for, and the plot's going to help me notice deviation from that. So I want the residuals to sort of randomly bounce around the zero line so that I know that my assumption that there's a linear trend is accurate. I want them to sort of roughly form a horizontal band around this line so that I know that the variances of the error terms are equal. And so I have in my head, this idea of what it should look like. I want, the zero line to be near the middle, so I know that there's not necessarily bias. And so, you can imagine I'm comparing this, and the chart type, makes it very easy to detect some of these things, because the eye is very good at detecting deviation from symmetry. So I'm going to notice and be very sensitive to the fact that this line is not exactly in the middle. It's easy for me to detect that perceptually. And so the idea is that, we're comparing, we're seeing maybe the deviation here. I'm just focusing on the deviation in terms of where I expected the center line to be, or the zero line, versus where it actually is. Similar to this analogy of a hypothesis test, we could even say that, I have some idea of the distribution of deviation that I might see with data like this, and I want to basically almost do a t-test and almost figure out a p-value here that represents how much I've learned about this deviation from my visualization. The gist is just that we have expectations, we compare them to what we see implicitly. Not everybody's going to do this in the same way. And in some cases, what people do might not really fit this analogy of a pseudo-statistical model, but that's okay, because the theory is meant to give us sort of a useful approximation that we can brainstorm from, not to be perfect. And so that's the high level view. We can formalize this idea of model checking in various ways. I already talked about how one way to do this is say that, when we're examining graphs, we're doing actual null hypothesis significance tests. But the way we frame it in our paper is slightly more generalizable way to think about it, which we think better stresses this idea that when we use visualizations, it's not just to ask a question is there a difference, but it's more to know how much of a difference there is, or how much deviation there is in what we see based on what we expected. And the way we formalize this, it comes from earlier work that Gelman's done, is basically to say that, we can think of our expectations for data that we're comparing to the visualized data as coming from or being generated from a posterior predictive distribution. In Bayesian inference, the probability, of y given theta times the probability of theta, which I have over here, is kind of an approximation of our posterior beliefs about the parameters that we're trying to estimate from the data. And so we're going to add to this probability of y rep given theta, which makes this basically a posterior predictive distribution. And the posterior predictive distribution is different from the posterior in that, like, the posterior distribution is in terms of the parameter. So, if I have some sort of line chart, the parameter might be the slope, whereas the posterior predictive is actually giving me the predictions based on what I've learned from the data in terms of data space. So you can think of it as sort of a reasonable data generator. So I have, some posterior predictive distribution. I'm imagining draws from that distribution and I'm comparing them to the visualized data. And that's kind of what represents my pseudo-statistical model. So no worries if you're not that familiar with posterior predictive checks. I'll say a little bit more to try to make this more concrete. But at a high level, the idea is that we're doing like a Bayesian model check when we look at graphs. And thinking of the visual analysis in this way can help us identify immediately some implications, such as, well, the more we know about the analyst's implicit model, the more useful we should be able to make the graph, because we can make it better, like perceptually optimize it to support finding deviation from that model. And we also can say something about, well, what should affect people's implicit models as they're using visualizations. So things like prior knowledge, because we can think of a prior in terms of like calculating our posterior distribution, how the observed data are perceived, and in particular how well someone can assess likelihood from the observed data should matter. So things like the visualization type might matter, how variation or uncertainty in the data is shown might matter. Obviously, when we're aggregating data by default, we're not going to get much of a sense of variation or uncertainty. So we can think then about like, well, what are some concrete ways that if we wanted to make visual analysis tools better, that we could change them based on this theory. So thinking more specifically about what we can do, we make various proposals in our paper. One thing that seems kind of obvious is, well, if people are evaluating these sort of implicit pseudo-statistical models against data that they're seeing, well, we want them to recognize how much information the data provides about parameter values that they're interested in. We're sort of assuming they care about likelihood. And so one thing we should be doing when we're visualizing data for visual analysis is trying to push people to account for variation and uncertainty. So the simplest way to do this would just be, default to plotting the raw data in a tool like Tableau or Power BI or one of these. Like, don't default to plotting aggregates. In some cases, that might not be possible because you get, over plotting when you have a huge data set, or maybe the user wants to see some type of mean or other aggregations. And so, maybe we need to think about building in different representations of uncertainty, even when there is a need to see summary stats. This is an area I've done a lot of work in. I think my colleague Matt Kay spoke for this webinar a few months ago, maybe, and he talked probably much more about this. But basically, we've both done a lot of research trying to figure out, like, what are better ways to represent uncertainty than some of the standard techniques that we usually see, which we know people sometimes have trouble interpreting. So, for instance, many conventional uncertainty visualizations are hard even for researchers to interpret. There's been some studies showing, for instance, psychologists and other types of researchers misinterpreting error bars. When we assume a frequentist 95% confidence interval represents the interval in which there's a 95% chance that the true parameter value falls, like that is an incorrect statement. We're actually talking about our confidence in the procedure that produced the interval. So interval representations can have lots of issues. We also know that people's impressions of effect size are very sensitive to what sort of intervals they're seeing. So we've done some work looking at how, like, if you're adding intervals to data, it really matters whether you choose to show uncertainty in whatever the stat is, like the mean, or uncertainty representing basically a sampling distribution, versus uncertainty representing variation in the underlying measurement. People can be given information about the exact same effect or the exact same data set. And depending on what you visualize, even if you give them the other type of uncertainty in text, their perceptions of effect size are very strongly affected by, like, how big the difference looks in the chart. And we see this a lot with our research on uncertainty visualization. Like, people really rely on, like, the amount of difference they see in a chart to judge things like effect size. And And that's what makes me sort of nervous about things like aggregating data by default. There's other ways, we can plot probability to different visual variables like area or width at any given point on a violin plot, or opacity in a gradient plot. But one of the things here we have to be careful about is that a lot of times, the visual encodings that look the most like uncertainty are actually some of the hardest for people to decode or to accurately read the data from. So, if I asked you, what's the difference in probability from this point here on the y-axis and this point here on the y-axis, probably you'd have a hard time quantifying that. And that's one of the problems, or one of the challenges as well, with good uncertainty visualization. Some of my work has tried to think of ways, well, how do we show uncertainty in more natural ways? And I think some of this could be useful in some of these visual analysis tools. So kind of an out there idea, but what if we showed, the data using animated draws from, that we generate by applying non-parametric bootstrapping? For a simple example, like, the error bar charts I was just showing, we would actually see the data move. And this gives us a good sense of like, well, like how much can we extrapolate from this data? Like, rather than just seeing two bars representing averages, I have to deal with the fact that like, oh, based on my sample size, there's a lot of variation here. And one of the nice things about showing uncertainty or variation via animated draws from the underlying distribution is that regardless of how complicated our chart is, we can still apply this technique as long as we can animate things. So this is a more complex visualization where we have data about gender-based differences in test scores in English and math in a bunch of different schools in the US. And so, it's hard to just add an uncertainty representation to something like this because we're already using many of the good visual encodings. And so we can animate it, and people will definitely get a sense of like, oh, there's a bunch of error in this data, or there's a lot of sampling error. So that's one thing. We can better present uncertainty, and I think we should be trying to do this when we visually analyze data. Another sort of bigger point related to this, I think, is that we need to give analysts using these graphical user interface tools more support for reasoning about data generating processes as they're doing visual analysis. And, even though someone might be, interested in just sort of seeing what kind of patterns they have in their data, if you're not necessarily enforcing any connection between exploratory analysis and confirmatory analysis, I think that's where we risk building tools that lead people to sort of draw these spurious conclusions, think that they see a pattern, and then actually realize much later, after it's too late, that that was really just some noise in their data and they were being too sensitive. Great, for instance, if I could see something like a lineup when I use a visual analysis tool like Tableau or Power BI or Oracle Analytics or any of these things related to this idea from Booja and others. Maybe I have some jobs report data that I'm looking at. I want to maybe learn something by comparing it to like, well, what does my data sample look like relative to predictions from a null model where there's no growth trend in the jobs market? Or maybe I want to go beyond just null models and think about like, well, could I specify a model where there's steady job growth and see what my data looks like compared to those predictions? And this example is based on actually something the New York Times did with jobs report data to help people understand the implications of sampling error. But I think that the general idea is that it should be easier to see predictions from various processes to help us sort of learn about what our data says and what it doesn't. And currently, in Tableau and probably some of these other tools, you can do sort of rudimentary addition of like various types of intervals. You can show a median, you can show a mean. But I think really the point that we're making in this paper is that our emphasis is sort of misguided. Like we're really emphasizing the pattern finding stuff, and we're really under-emphasizing any kind of support to help people think about actual uncertainty or data generating processes. And so, just like, if you really wanted to, you could, do deep neural nets in Excel. I've seen people do it. No one really wants to do that because it's very hard. And so the idea is like, how do we make these kind of things more accessible? And related to that, one idea that I think could really be key is to realizing this vision of sort of supporting graphical model checking in visual analysis is to think first about how Tableau currently works and try to build on that. So a tool like Tableau, which is sort of, I talk about it a lot because it's the one that's most of these GUI tools, the one that's most based on visualization research. What's happening in Tableau is like you interact with variables and you can drag them to these shelves above your plotting area. And when you do that, Tableau on the back end is interpreting your interaction as a query. And it's basically on the back end has this table algebra, which interprets your query, as a database query. It's going to figure out how to show you data that you've said you're interested in. It's also using a grammar of graphics that states like what is a proper visualization, in this grammar. And so it's automatically recommending, when you use Tableau in this particular way, visualizations that are designed to be useful to you and also are designed to be perceptually effective to you. So Tableau has some built-in sort of knowledge about like what we've learned from graphical perception experiments about like how to best show data for accurate perception. And so one thing that I think would be really cool is to think, well, if Tableau's already, and these tools can already do some of this automated recommendation, why not extend that so that we can also, when people are interacting with data and making certain types of plots, be recommending statistical models that they might want to compare against their data or compare predictions from against their data. So you can imagine, just as an example, maybe I'm an analyst at a sleep tracking company. I have some data here on the left, which is hours of sleep per night from some sample of customers, and I'm interested in how that relates to the fitness level that people report who are using the tracker. And so I make this trellis plot where I'm splitting things up maybe by gender, by whether the customer has previously used a sleep tracker. I'm looking really at this relationship. And maybe, after I create this plot, I also add, trend lines to really see, like, are there any interactions here that are interesting between these variables? And if an analyst is making trellis plots, if they're adding things like lines of best fit, maybe that is a sign that they are interested in evaluating some sort of model, or they have some sort of implicit model. And so you can imagine, well, maybe what we should show them predictions, which we could animate in. This is just a few predictions, but maybe, we show them predictions from some model, a maximal model that contains or models, all of these variables as well as their interactions. And, if you make this accessible to an analyst, maybe, they notice right away, and they no longer waste time on this, that while they might think like, oh, there's a difference in slope direction here for this subplot, they might realize, oh, actually, there's a lot of variance in my data, and I probably shouldn't put too much faith in this. So I think thinking about like, how can we automatically compute and recommend these things could be useful. And of course, there's lots of user interaction design that would need to go into this, because you don't want to overwhelm people. So it would have to be sort of something that, you expose to people gently. You have to give them some ability potentially to customize, like, do they want to include interactions? Do they want to see predictions of a model without interactions, et cetera? But I think the idea is sort of an interesting direction. And going along with that, letting people customize things. If we're analogizing visual analysis to a posterior predictive check, then we should assume that sometimes people will have prior beliefs that are important. Maybe in some cases, analysts, are using visual analysis tools to repeatedly analyze data of the same type. So I think a lot of like business intelligence analysis is like this, where, I'm always looking at, marketing data, and I'm just getting like new data over time. So there's ways that we could think about building in priors or learning priors over time, so that we can help an analyst realize like how much new information does this new data set really give me over what I've seen before. We could elicit directly priors. So I've done some work related to, how do you elicit a prior in a natural way that people seem to understand? So we've done sort of distribution builder based interfaces. There's also, similar to sort of showing uncertainty by animated draws, you can imagine eliciting certain types of beliefs for more complex data sets or more complex visualizations, like doing it graphically. So here, if I want to get some sense of someone's prior on slopes and intercepts in this visualization, I can have them basically give me a set of representative samples, and I can try to infer something from that. And so once you get a prior, you can also, in addition to, incorporating this into model predictions for a posterior predictive check, you could also, this should say prior, you can also do a prior predictive check, where I'm going to visualize draws from my prior against the data to make sure that, like, I'm telling the tool what I think I'm telling it. So yeah, typo on that slide. So those are just a few ideas. Of course, there's plenty of challenges with this proposal. Like right now, I think, like I've said multiple times in this talk, the way we build visual analysis tools, we're really assuming that sort of we don't want to overload the analysts with any extra information. We really just want to make the patterns pop out as much as possible. And so, there's lots of challenges, like how do you integrate this kind of tighter integration with statistical modeling and modeling checks in ways that's not overwhelming, that's not giving people tons of like, text-based menus to navigate through. Like how much can we use graphical interfaces to do this, to make it more natural? There's also challenges, how do we ensure that some model can be fit? And realistically, you're not going to be able to, in real time, fit any particular model that someone tells you they want to see draws from. You have to constrain it and potentially use analytical solutions. But I think it's worth exploring, what can we do that could be useful. And finally, this notion of simply cognitive load, I think, is really important. Doing data analysis is already hard. So how do we avoid overwhelming people? And what's the right balance between like recommending some of these things because we see someone, like putting trend lines on their chart, and so we think there's a model, versus making the analysts find these things, which is closer to what current tools do. Open questions. I have one more slide just to wrap things up. So, I presented a bunch of ideas of like how we can think about visual analysis and how that can inform the way that we use visualization and how we can make visualizations and visualization tools better. But I think like just sort of to end with kind of a broader point, I've talked about this specific theory that, we can liken visual analysis to a posterior predictive check. But I think there's beyond any specific theory, like there's a room for more theorizing just about visualization and about how visualization works and specifically about what kind of problems we are solving with visualization. And maybe, my proposed framework that I've talked about today is not the right one. But I don't think we're going to get very far if we don't continue to try to sort of propose frameworks like this and propose theory. And so I'll end again with this idea of like we need to understand what sort of problems we're addressing when we're dealing with visualization, so we can begin to make clearer predictions, for instance, about like when is relying on aggregates and relying on sort of simple heuristics that we might use, like how big is the difference between these two means? When can we expect that to work? Versus when do we really need to be following things up with confirmatory analysis and pushing, users of tools to follow things up? And so, I think something we don't do a lot in visualization research is really define like what are the data generating processes that created the data that we're showing to people? What kind of signal to noise ratios do we think we're dealing with? And of course, in a lot of real world settings, like how much it matters whether you follow your visual analysis with some more formal confirmatory statistical analysis is also a function of like how important the results of that analysis is. And so we also, I think in real world visualization scenarios, we have to be thinking about like, well, what's the utility function? What's the payoff function? So, I shouldn't be relying on like a difference in means to make this important choice about like, or to make this choice about, should I invest in this stock or this stock? But if I expect the payoffs to be roughly the same, whether I make a wrong choice or a right choice, like maybe it doesn't matter. Even if I have some noise and confounding, maybe I can just use visualization. And so I think there's a lot of interesting questions about like when can we expect visualization alone to work and why not? Recently, I've even been thinking about things like we use in computer science, these complexity classes to talk about algorithms, like how, what amount of memory or time resources does it take to solve a particular problem? I think we could similarly think about visualization problems this way. So, maybe certain problems, data problems, can be answered using visualization alone, but how many different types of trellis plots do we need to make? How many visual comparisons do we need to make in order to do that? And can we think about sort of benchmarking different types of problems to get a better sense of how important visualization is or how important statistical modeling is? So, all right, I will end there. I have a lot of students, both current and former, and collaborators at various work that I've talked about. So thank you to all of them. And thanks for your attention. Happy to take questions now, I guess.
Thanks, Jessica. That was great. So we have a few minutes to do questions. So let me start by just asking you kind of a meta question in terms of where do you see this field? Like what is it, like a state of maturity of this field now, right? Like I remember seeing, I think it was from your paper, you mentioned this Prim9 system for data visualization that was done by Tukey, I think in the 70s, where he had like, for the time, really neat kind of, he showed like a rotation of data through several dimensions. And it was like a computer that was built just for that with like specialized buttons. It was like a crazy thing. And then, we definitely made a lot of progress, right? So you showed some example of Tableau, but there's ggplot, there's lots of tools, right? So the field had matured, right? But it's sort of hard to tell, at least for me, as I'm not a specialist, is like, are we like approaching an area where like most of the things sort of the easy things have been done, or like how much is left? Like, where do you see this thing sort of now relative where it was and relative to what it actually reasonably could be in some years to come?
Yeah, that's a great question. I hope not a lot of people from my field are listening, because I don't want to make anybody angry. But I mean, I guess I talk pretty openly about these kind of things. Like, I think always been very problem oriented. And so, we're always solving like new little technology based problems. Like, how do you enable quick interaction in the browser with huge data sets? Like, that's the problem that is not really solved. So there's a lot of that, like how do you, like I said, some of these behavioral optimizations, like how do you use speech, et cetera. And I think one thing that we've done a lot since like the Prim 9 days is there's been this huge explosion of like different visual encodings for different types of data. So like when we're dealing with genomic data, like what's the correct set of like visualizations and interactions that allow geneticists to answer certain types of questions. So there's tons of like these domain specific discoveries happening all of the time. I think what I worry about is sort of like we're extremely empirical as a field when it comes to like understanding what makes a good visualization in more general ways. Like our sort of base of knowledge outside of these very specific problems is really based mostly on sort of like, let's do an experiment and see what happens. And so I think like there's probably some stagnation in my opinion. And I think, part of the reason I, in a lot of ways, am moving away from visualization in terms of research is that if you're not just about solving these little problems and there's tons of like work to do in terms of, like creating better, easier to use software packages. Like, I'm not saying that is not hugely critical work, but things like, MatK and others are doing for plotting in R, for instance, like I think that's really important. But in terms of like, sort of what are the hard problems in visualization that are not just about like making things easier, I think I've gotten a little disillusioned because I think, well, we don't have any theory. And so like, are there any like grand challenges in visualization? And in particular, doing all this work on uncertainty visualization, I think like uncertainty and how to present uncertainty and help people reason with it has always been like this sort of underemphasized area of visualization research where, we just think of it as not really core to visualization, which is a weird thing. But the more I've done it and tried to like make it more popular, on some level, I think there's been a lot of progress there. But at the same time, I sometimes worry like, how do I really know, when it's important to add some uncertainty representation to some plot of aggregates? Like in a lot of ways, I think without any theory, we don't even know how good some of these like heuristics that people are already using work. And I tend to think it more and more that like a lot of times the visualization doesn't really matter. Like when we do our experiments, we often isolate these like small regions of the possible, space of data that you might be working with, and we find effects within this like very tightly controlled region. But I think in a lot of cases, it actually doesn't matter as much as we think it is. And so that's why I think like thinking more about like what are the data generating processes we're dealing with, what sort of like payoff functions, like what's the real world importance of this data problem, like that. I think people in the real world could be helped by that, like to know like when do I really need to worry about this nitpicky thing, and when do I not? So yeah, I think, the field's making progress, but it's also in some ways, I feel like hitting a roadblock because we just don't have any theory.
I see. So you think the progress to make, sort of qualitative progress, you should develop some theories. It sounds like what you're implying.
Yeah, figure out, what problem are we trying to solve beyond these one-off
Makes
things?
sense. So Robert McDonald asks sort of a question that I also was thinking about, which I think is relevant here. I wonder your views on it. An audience to whom you're communicating is obviously important, and how well the information that you're sharing is perceived would sort of depend on that audience. And in particular, like David Spiegelhalter recently has been doing a lot of work in trying to communicate uncertainty and data to lay audiences, right? So he's concerned with like very non-statisticians, everyday people just trying to like make decisions about their daily lives, about their health, and so on, right? And then there are also expert audiences, right? That other statisticians or someone who's just an expert in a specific domain. So Robert here is asking, like, how similar or different are the visualization needs between these groups? And I would add, is it useful to think of them, you think, as sort of a separate, or would a general theory apply across?
Yeah.
Or what's your take on that?
I mean, I think for the stuff I talked about today, and really a lot of my work has tried to like broaden the idea of like, uncertainty depiction. And now in this most recent paper, like really thinking in terms of data generating processes in general, and doing model checks like to more than just the people who already know how to do these things. So I think like, yeah, I think like the broader audience stuff and the public, like a lot of my work on uncertainty visualization has focused on those groups. I think, in the kind of stuff I talked about today and really what I've been thinking about, with this particular paper, it's who are we building these graphical user interface tools for? So like we know there's statisticians, people who are always going to go to R or like Python if they're doing whatever machine learning. In a lot of ways, like the visualization research community is not building tools for these people, or we are, but like we're when someone knows how to program exactly what they want, it's a totally different ballgame. And so what I'm talking about today really is intended, I think, as this question about like, can we go further for people who are not necessarily going to follow their analysis in Tableau up with anything else? What would it look like to help them do a little bit more sort of checking of what they're thinking they see in the data against like something that's actually well-defined statistically? And so I realize that's like a huge challenge. I think what I've seen with uncertainty visualization is like there are these sort of hacks you can do that can take something complicated, like, uncertainty of some type and help people understand it. So things like showing people draws from a distribution rather than trying to represent the whole distribution. Like we see that like sometimes these analogies help people, better understand it. And so I think, I am interested in people who don't have like a formal stats background, but who have somehow found their way into like data analysis in some way or another. And I have some experience, like even in my own past, like what is like people that are sort of in that camp doing data analysis. And so I'm really sort of interested in how do we gently sort of push people to think a little more formally and check their intuitions. So it's a good question. I'm not necessarily with this stuff, like with the thinking about like, how can we make a better graphical user interface system? I'm not necessarily thinking about people who are like statisticians because they know what to do. I think some of our work applies there too, because it's like giving a more clear understanding of like how graphs function in those settings as well. But in terms of like actual design implications, I think I'm focused mostly on these like broadly available visualization tools.
So another question from Eric Moore is saying, is it interesting to think about explicit articulations of subject matter knowledge for model checking? The Hullman-Gilman paper mentioned knowledge graphs. Is that an active research area somewhere?
Oh yeah, so in the paper we have this section where we talk about, like if you were going to make an artificial intelligence to do model checking using visualizations, like how would you go about that? I think that's where the knowledge graph comes in. So on the one hand, like, this one of the things I worked on a lot over the past few years, like 5 years, has been like, how do we more explicitly integrate people's prior knowledge into like data analysis? Because the way we build these systems and the way we think of visualization, it's like everything remains implicit. And I might have I might have like worked with data like this often, but we don't really support like in any explicit way, like combining what we know from the past with what we have in this current data sample. And so some of the work is very much, or some of the work I've done is very much looking at like, well, how feasible is it? Like, can people articulate a prior, like, and again, like thinking about non-statisticians, but also I think like, there's a lot to do in terms of like, can we learn priors automatically as people are using certain visual analysis tools? Because we are often interacting with the same types of data repeatedly with like small changes. So like on the one hand, there's the user interface and there's prior elicitation and there's lots of interesting things you can do there. It's hard, but worth exploring. On the other hand, like, like I say, we have the section of the paper where, we propose that you could, by trying to sort of think about like how would an AI do a model check, like how would they go through this process, like this Bayesian, statistical workflow that, Andrew and Aki and others have written this paper, about like how do visualizations fit in. Like if you try to actually think about like how would you automate that, there might be things that we learn. So the knowledge graph part is related to that. Like, can you can you sort of formally represent what's already known, and even like what people look for, like what sort of associations they have with different graphical schemas. Like, I don't think we're there yet in AI, but I think, the idea is that thinking this way might be insightful. There's a lot of work in like automated auto ML right now, which is kind of like, how do you just, you start with the data and that's all you need, and your auto ML system will spit out answers, and the actual ML engineer no longer has to make any choices about models or parameterization, et cetera. If you actually look at that research, like it's not auto by any means. There's still a lot of guidance that needs to come in. And so I think there's an interesting question in terms of like, well, how much of this just like basic inferential data analysis process could we automate? And could we ever automate this sort of like visual check part of it, or is there always going to be something that's just hard to get out?
Gotcha. So a slightly different topic. So an area where we work a lot, which is in early oncology trials, we have sort of an opposite of a big data problem, right? Where instead of like what a lot of people have, like very large data and then lots of simple models, we have relatively little data. But like our posterior is huge, right? And so we have, in the order of 10,000 parameters. And, people who work in Bayesian inference today, they often find themselves in that space, right? Because the tools like Stan and others are now, they're letting us fit these very large distributions, right? We struggle a lot with, how to navigate that large posterior distribution, how to show the right parts of it and so on. You can't obviously show everything. The question I have is, is it useful to think about like visualizing raw data in a different way from sort of visualizing the inferences? And I know you make a connection there by kind of overlaying some model structure on top, right? You can show posterior predictive distribution and so on, but when your parameter space is very large, right, you almost like do an exploratory analysis on the model space, right?
Yeah.
And like, do you have any thoughts sort of on that? Has there been research in that area, or?
Yeah, I mean, I think like in visualization research, there's been this push in the last 5 years, like in every field, to like, how can ML be relevant here? And so there's been like exploratory analysis for like machine learning, like, big neural net models, like how do you make sense of the results there? And so there, I think in a lot of ways there you can get away with some of these like sort of standard, like how do we make a good visual interface for exploratory analysis? Like if you're assuming, I don't know who's looking at these posteriors that you're creating or whatever, but if you assume that someone has knowledge of the model, then I think like the bigger challenge is just like, how do you reduce the cognitive load, as they're looking through all this? Sometimes in some of these like ML-based visualization interfaces, I think they could do more to differentiate like what's the input data, like what's the raw data, and what are the model predictions. But I think some of the things I talk about are sort of less relevant there, just in that once you, like there's this constant balance between like cognitive load and visualization and like more uncertainty. I think that like a lot of my work is always trying to find the right balance. It's like we can't default too much to like reduce the cognitive load completely, and we can't default too much to like overwhelm people with uncertainty and variation in statistical models all the time. And so I think like from what you described, it sounds like the first step is, make interfaces that somehow handle this cognitive load aspect, that make it easy to search for things, that make it easy to begin to see patterns. So I don't know how helpful that is. But
that's helpful. Thank you. That makes sense. All right. I think that's all the time that we have. Thank you very much once again for coming and
thanks for having me.
Yeah. And we'll see you guys again in July. Okay.
Cool. Bye. Thank you.
Thank you.